whatever, you know, of course you can think that you have a large-scale toroidal component, but on the other hand, in general, I haven't done the calculation, but it depends on what is exactly your assumption for the magnetic field configuration. And since you are dealing with reconnection, which intrinsically is a process that changes the overall magnetic field geometry.
Basically, is a photospheric emission. Photospheric emission. So there are many scattering. So on the other hand, the magnetic field produces polarization. On the other hand, photospheric emission produces normal polarization. I'm just wondering.
Yeah, I haven't thought enough about it.
Okay, thank you. Okay, and then the final talk of this conference is by Switzerland. We'll be talking about something that we don't have in the program.
No, no,
Komsky or not to IC. Okay, so we will tell us.
I decided to give a theoretical experimental talk. And experimental, I mean that I discuss various topics which have nothing to do with the title. So the real title is To IC or Not to IC and Other Questions on GRBs. And I'll try to discuss 4 different problems. I most likely won't get onto 2, but we'll see what we can do in this remaining 10 minutes that I have. The first one is just some remarks on new results on the luminosity and the rate of gamma ray bursts. The second and third are related, is the general question of inverse compton in GRBs, and in particular, what is the origin of the prompt emission in 080319B. This is very related to the 2 talks that we had earlier. And the last talk, the last issue is related to the previous talk, and this is the idea of relativistic turbulences, an alternative to internal shocks. So very quickly, the first issue. By now we have a large compilation of bursts with redshift and luminosity measurement from SWIFT, about 100 bursts. And this means that one can try to do the exercise and invert this data directly and get both the luminosity function and the rate. To do so, you have to be slightly careful. The data that we have is composed of 3 different sources of redshift estimates: emission lines from the host galaxy, absorption of photometric directly from the afterglow. It is clear that we have to throw away the subgroup with emission line from the host galaxy. It's misleading. We have to keep only the ones which are obtained directly from the afterglow. Then you get a uniform sample, and this is more or less what we see from the sample. This is luminosity, and this is redshift, but it's distorted. The scale here is distorted. It's not linear. I'll explain later. And we have to make one assumption, and the assumption is that the luminosity function is independent of the redshift. In this case, we can write such a relationship that the number as function of L and Z is the luminosity is dependent on the luminosity functions times the rate. And if we do this, we can take this distribution and simply invert it. And when we do this exercise, we get the following distribution. This is the redshift distribution at the source. This is the observed redshift distribution. This is the luminosity function at the source. And this is the observed luminosity function. And what I want to stress here is that this luminosity, this rate distribution is very different from the star formation rate. It is constant at large redshift, but it begins to drop at around 3, whether the star formation rate begins to drop at around 2, and the decrease is less dramatic than the usual star. It's comparable, but slightly less dramatic than the usual star formation rate. But the most important factor is that for the star formation rate begin to drop somewhere around here. It looks like a small difference on this graph, but it's a very big difference. And I can tell you that if one tried to enforce that the GRB follow the star formation rate, then one cannot find a consistent solution unless one assumes that the luminosity function evolves with time. This is not impossible. It is possible that the luminosity function evolves with time, but in my guess it's less likely. If we accept these two results, then the conclusions is that one of I mentioned luminosity function do not follow the star formation rate. The local rate is between 0.4 to 2.6 gigaparsec minus 3 per year. Comparable to previous estimate, this is the canonical value around 1, more or less what others have found before. The fact that there was one burst at redshift 8.1 is completely consistent. This is the 8.1 redshift burst. The fact that, and this graph was obtained actually before this, without using this data point, or before using this data point. This data point does not make a change here. So having one burst like this per 4 years is perfectly consistent with this prediction. This means that we'll have to wait another 4 years until Swift sees another one. And the last point is that the lowest energy burst in this sample has 5 times 10 to the 49 ergs, and the burst 060 which is 10 to the 46 ergs or so, must belong to a different population, which is very, very large if it's typical. Okay, so this is the first thing. The thing to remember is that GRBs do not follow the star formation rate. It's consistent with many other earlier work, including work by Dane and Mochkovitz and a few others that I don't cite here, so I apologize for that, but it's just a confirmation of this result. But what we have is this robust estimate here of what is really going on. Okay, now to the question of IC or not IC, inverse Compton or not inverse Compton. And this is motivated by this naked eye burst and prompt emission, which seems to be in optical, which seems to overlap the gamma rays. And the initial idea was that this is the gamma rays are the synchrotron self-Compton of the optical. So first, if you look at the light curves, and now there are better light curves for the optical, it's unpublished, but there is a clear time delay between the optical and the gamma rays of a few seconds. The optical lags by about 5 seconds after the gamma rays. So this is already indication this is not inverse Compton. So, but before getting to these birds, I'll ask some general question. What's happening in a typical GRB, not in this one, which was very peculiar. So if the inverse, if the gamma rays are synchrotron self-Compton of optical or infrared or UV, then we have this amplification here from this low energy emission to the soft gamma rays, but then there will be a second component with a comparable amplification, unless we are here in the Klein-Shiner regime, in which we have a somewhat weaker amplification. So the question is, but we expect a second component around 500 GeV, could be lower or higher depending on the parameters. But the point is that we have on the prompt optical, we have strong limits for typical bursts. It's usually larger than 12 magnitudes, and in many cases it's even weaker. So we have an upper limit here on this value, and this actually puts a lower limit on how much amplification you need from here to there. At the same time, there are upper limits already from Egret, but definitely now from Fermi, on how much emission we have at very high energies. And we know that we cannot have at very high energies more energy than in this component. Probably the right guess is that we have here at very high energy about 1/10 of this component. So this puts a limit on this amplification, and if we have a limit on this amplification, we have a limit, and we have a limit on this amplification, we can find inconsistency. And this is this. So this is here the summary of the inconsistency. This is the high Lorentz factor, y high, and we know that this y high should be less than 1. So what we do here, we use the limit in the optical, and depending on the peak frequency, this is the peak frequency of the low energy component. It could be in the optical, it could move to the UV, or then the limits are weaker, or it can move to infrared. Again, the limits are weaker because the strongest limits are in the optical. So using this, we can estimate how much is y high, and since we know that y high is less than 1, we see that most of this region is ruled out, and we are left with two possible limits, two possible regions, which will be also ruled out. One is the UV region, and this is ruled out by X-ray extrapolation. This region is so close to the low energy X-ray, and that we extrapolate down from the low energy X-ray, we can rule this out. And this optical, this infrared region is ruled out because in this region, it's very typical, energies are very low of the photons, and you simply are limited by self-absorption. So we cannot have so much energy as a seed photons coming here because of self-absorption argument. And this is a second way to look at this the same graph. The situation depends on the bulk Lorentz factor and on the Lorentz factor of the electrons. This is, by the way, something like here around 200, and Lorentz factor of few hundred. This is the canonical range for internal shocks. It's completely ruled out. What you can have is either extremely high Lorentz factor of the electrons. This will correspond to the infrared solution, but I said before it's ruled out by self-absorption, or very low values of gamma E, less than 100, and this will correspond to a UV solution, but here there are problems with extrapolation down from the X-ray. So this shows that it's really unlikely that what we find is what we see in the soft gamma rays is typically synchrotron self-Compton. And this is, in a nutshell, this is sort of a back of the envelope summary of the calculations that have been shown earlier by Frederick Dane. So this is the self-absorption limit. I don't have time to go into details. Another problem which can occur here is pair avalanche, which complicate the situation, but I won't go into it. So the second conclusion of the second part is that most prompt soft gamma ray emission in GRBs non-authorized from synchrotron self-Compton. Actually, I never said synchrotron self-Compton. It's any self-inverse Compton process does not work here. And I want to stress that this analysis was very, very general. I did not mention internal shocks. I did not mention the specific process that generates the relativistic electrons, or I don't even mention the typical angular timescale delta T larger than R over C gamma squared. So I was really asking a very, very naive question. Take a bunch of relativistic electrons, let them move with the bulk Lorentz factor gamma, let them have their own internal Lorentz factor lowercase gamma, and let us use the limits on F gamma and F optical and see what is going on. And the answer is that because of the limit on the optical and of extrapolation from soft X-rays down to UV, it is unlikely that it is inverse Compton. There is a caveat here. I didn't discuss external inverse Compton, but similar arguments are probably relevant to external inverse Compton. It is more complicated though. Okay, now this work was motivated by 080319B. So what about 080, what about this one? Here the prompt optical was very strong. It was 5th magnitude. So the limit is disappears. And does this solve the problem if I take out the limit of very small optical, very low optical emission? So this is a schematic diagram of what we know about the spectrum of this event. This is the this is the gamma rays. This is n to the minus 2.6. This is n to the 0.2. This is the unobserved spectrum. So here we have much more information. We know what is the shape of the spectrum. We also know that there is no break in the spectrum of a factor of 60 down from the synchrotron peak, from the peak here down to about 10 keV, which is the low energy range of Swift. But so we know that there is no place for a break here. So we can use now this spectrum and try to ask. And we know also what is the peak of the optical. So we know we have a value here, which is the peak of the optical. We don't know, assuming that this is synchrotron self-Compton, we don't know where is this peak here. So this is a free parameter, but we have a limit because we know exactly a value here of the optical. So now we can start to play, and by playing I mean we can move this, we can shift this spectrum up and down, keeping this place always at this point, and we can try to see whether there is a consistent solution which is consistent between, which is give a consistent thing without overproduce. Always keeping in mind one thing, that you don't want to overproduce too much very high energy component. When we do this, the basic problem is the optical. The optical is very powerful, and the optical must be less than the black body emission. This is just a usual limit. We cannot emit more than black body. So this puts a very strong limit on the emission radius of the optical, which is also related to what Frederick was saying, that this optical must be emitted at very large radius. And this is the essence of the problem, that this large radius is problematic. But we can continue the game and find that the optical, the black body emission divided by the optical emission is 2 times 10 to the minus 3 times. Why is this high Lorentz factor, which we want it to be less than 1? F is a filling factor, and gamma 3 is the bulk Lorentz factor. And we want this to be larger than 1, so you see that unless y is very large, this cannot be larger than unity unless we have a very large y here. And this is again this problem that synchrotron emission, synchrotron self-Compton does not work here. We can try something completely different, and something completely different is two populations of synchrotron emitting electron located in the same place. So suppose that we have a double-peaked electron distribution with low energy peak and high energy peak, and we'll say that this is producing the optical, and this is producing the gamma rays, but by synchrotron, by both sitting in the same place. and the same radius with the same magnetic field. If it's the same magnetic field and the same radius, we can relate the fluxes, and we can see that unless this component is huge, contain huge amount of energy, this does not work. And this will be again a very, very wasteful solution, because we'll have a component which really contains most of the energy, but it is not emitting because this is in a slow cooling phase. It doesn't work again. So the bottom line conclusion here is that first of all, this is not synchrotron self-compton of the optical, and again, this is it is very consistent with the fact that the two spectra, the two light curves do not overlap, because after all, if the optical is the source of the gamma rays, why is not tracking why one is not tracking the other? So this is conclusion number one. And conclusion number two is that the gamma rays and the optical most likely did not come from the same emitting region. And again, this is just supporting what was found by Frederick and his group, that we need two different emitting regions. It can be either two different internal shocks, one taking place at larger radius and one taking place at smaller radius. The optical should be taking place at larger radius here, and the gamma rays at smaller radius. I don't think that the possibility that the optical was produced by external shock was sufficiently systematically studied to be ruled out. This is another issue. I don't say that I have an external shock, reverse shock model which is working, but I think that it was dismissed too quickly, and given the problem with the synchrotron self-compton and these two issues, I think that we should go back and study carefully this other possibility. Well, I have 5 more minutes, so I'll very quickly go over the last topic, relativistic turbulence. Now, relativistic turbulence was invoked as a way to overcome the problem of light curve variability in the GRBs. To remind you, if we have external shocks, we have 3 time scales, and all these 3 time scales are comparable. One is the acceleration time scale, one is the two time scale. One is the angular time scale, and the second one is the acceleration time scale, and both of them are the same. And because of this, we cannot have variable bursts. We can have only bursts with single peak. Things go up and down on the same time scale. So this led to the idea in the late 90s, that if you have such a variable light curve, this light curve cannot be produced by external shocks. Now, a suggestion to overcome this was to add, on top of the bulk Lorentz factor that we have here, regions within the emitting region which are moving relativistically in the local frame. So we have now 2 Lorentz factors, bulk Lorentz factor gamma, which is sort of global Lorentz factor, and the turbulent Lorentz factor gamma prime, in which some subparts, some blobs within the shell are moving now with macroscopic relativistic velocity within the shell. If we have such a structure, then when we calculate the global time scale for the acceleration, it will still be r over gamma squared. But the variability time scale has now 2 factors which appear here, 2 new parameters. One is gamma prime, and the second one is psi. Psi is the angular size of this region, of this blob. And so you have 2 free parameters here, and if you have these 2 free parameters, you can play as many games as you want, and you can get this into a situation that t is large and delta t is small, and it seems that one can resolve the variability problem by invoking such a structure. Now, I won't go into the details of this algebra here, but there are two constraints that we have to take into account. First of all, we know what is delta t over t. So we have one condition. We know what is the ratio between the variability time scale to the total time scale in different layers. The second condition that we want is we want the situation to be efficient, and in order that the situation will be efficient, our psi, this puts a limit on psi and gamma. Psi, which tells us what is the size of the angular size of each blob, has to be such that the whole shell is covered. If the whole shell is not covered, we will have regions which are not emitting, and we'll get back to the inefficiency problem, which was a problem with external shocks. So with these two conditions, we can set and we can actually calculate what are the needed values of gamma and the turbulence Lorentz factor and psi, and these are all observed quantity. NP should be of order unity to get a full coverage. T over delta T are known, and F is a filling factor which should be also of order unity. So we can calculate what is gamma prime here. We find it's about 10 and so on. I'll skip this. I just show that there is a second version of this turbulence in which instead of just motion, you invoked here that what you have here is regions in which reconnection takes place, and the physics is slightly different, and the mathematics is slightly different, but you can work out also what is going on here. Also here you get conditions on the relationship. What is the problems with this model? First, you have to answer a deep question, how you have to convert a lot of energy locally to this turbulent motion. A gamma prime should be of order 3 to 10. This means that locally, in the local frame, you have to convert about 90% of the energy, between 2/3 to 90% of the energy, you have to convert to kinetic energy of these blobs. How do you do it? It's not clear that is known. There are some technical problems with fitting the light curve, and the most serious problem is that these solutions require, all the solutions require some ad hoc combination of this ad hoc relationship between this value psi and gamma, which are not, do not necessarily arise naturally. So it's true that this model can work, and here we have some light curves which simulate this. For example, this looks like a very nice GRB, or this can look can also like a nice GRB, and these are, they are efficient, but you have to but they are sort of ad hoc solutions. So to my great surprise, I managed to say almost everything that I wanted. And the last thing is that I want to advertise two conferences, actually a conference and a winter school that will take place in Jerusalem, both in December. This will be a winter school, so students here are most welcome, and if you have students that are not here, you are welcome to send them. This will be a 3-day conference, a 4-day conference. And there will be 1 week between them, so you can travel and see the Middle East in between. And then enjoy Christmas in Jerusalem.
Thank you very much. Questions? Okay.
This Lorentz factor of turbulent motion of between 3 and 10 would mean that if it's a pure Hydra case, then it's supersonic.
Yes, yes. I don't.
That sounds to be odd.
My attitude to this model was not. I'm not advocating. I am just trying to see what are the conditions for it to work. And what we found here is the set of conditions on the parameter that show if you want this parameter to work, you have to tell me how to generate such a turbulent motion. I completely agree with you that it is Actually, there are two versions here. One version is this just pure turbulent motion, like this hydrodynamic turbulent motion. Personally, I think this is really less likely. This is what you're suggesting. The second model is this relativistic reconnection, a magnetic reconnection. This makes more sense physically, but it requires even more fine-tuning of different parameters.
But even here, it's not clear that you get relativistic motion.
Excuse me?
It's not clear that you get relativistic motion even here.
Even here, it's not clear that you get relativistic. I agree with you. I'm not trying to advocate this model. I'm just playing this game trying to see what are the parameters in order that this will work. And I'm telling anybody who is invoking this model as a physical model, show me how do you get this parameter.
Well, in fact, in this case, the outflow speed in the jet is about the Alvin speed. So if Alvin speed is highly relativistic, that you easily get high Lorentz factor.
Yuri Levansky in 3 dimensions showed that it's difficult to
if it's aligned and you get there, you effectively convert
It has to be exactly
pointing flux into the kinetic energy flux. If it's not aligned, then it's pointing flux into pointing flux.
Yes, it has to be if it's exactly aligned, you can work it out.
it's quite good.
Okay.
I don't say it's not.
More questions. Lucas.
You mentioned something about the Ferrier range. Could you comment about some Perkins case you mentioned?
Yes.
Could you say more about this?
Not much more than just the fact that this picture that I showed here is complicated if you get into this regime. If here you are in the Klein-Egina regime, then these photons that you are producing here are energetic enough to interact with these photons here and create pairs. And then you begin to create pair avalanche. Then you begin to create more and more pairs. And depending on the time scales of creating these pairs, you may generate a huge population of electron-positron pairs, and then what's happening, you shift all these frequencies down and you change the structure. So you have to take it does not solve the problem, it just makes the problem even more complicated.
And the parameters are such that it's not enough to sustain development?
This I'm not sure.
Okay.
I'm not sure that what is the time scale, what are the time scale. But if it develops, it makes the situation even worse.
We'll need to do more detailed calculations.
I just would like to remind that power density spectra of complex logic reverse are parallel and pretty wide, and moreover they have a slope like Kolmogorov spectrum, and I think that's support for such concept that is from local motions or connections.
Okay, then let's take 3.
I want to use the fact that I'm the last speaker and thank the organizers.
No, yes, I will.
You want to take
I will tell you. Before we conclude, of course, the important thing is that at 2 o'clock we have lunch. Yes, and then before we conclude, I need to mention a few things. So we would like to thank sponsors, and sponsor is Vetenskapsrådet, which is the Swedish Research Council, and Nordita, also the second sponsor who sponsored this conference. I would like also to mention the organizers. I'm not one of them, so I'm not thanking myself. So, and the organizers is the Stockholm Observatory, the Heinrich Astrophysics Group at Stockholm Observatory and Royal Technical School. And especially, I would like to, and of course there are secretaries there at the observatory, at Nordita also that were involved in that. And especially I would like to thank Magnus Axelsson, who is sitting there, who took care of most of the organization here, and Shane Maglin, yes, who is also involved very much in that. And so those 2 people made this conference a success, I think. And so I would like to thank them.